Hi. In this video, we are going to start a new section for the course, which is on arithmetic and geometric sequences. So the basics of arithmetic and geometric sequences should be familiar to all of you students. The idea is simple. An arithmetic sequence is a sequence such that every term is the difference between any two consecutive terms is constant. So let's say we have a sequence like this. If P, Q, R, S are positive integers, if P, Q, R, S are positive integers, then P plus S is equal to Q plus R if P plus S is equal to Q plus R, then we have AP plus AS is equal to AQ plus AR. So what does this mean? So when we write this notation of a sequence, we are saying that this is a sequence of numbers like this, A1, A2, and so on, AN, and so on. And the arithmetic sequence has a property that A2 minus A1 is equal to A3 minus A2, and so on. And that is known as the common difference, right? Now, P, Q, R, S are positive integers, and P plus S is Q plus R. What is AP? The general term of an arithmetic sequence is given by A1 plus N minus 1 into D. So therefore, AP would be A1 plus P minus 1 into D. This is the Pth term of the sequence. This is the Sth term. So AS would be A1 plus S minus 1 into D. And similarly, Q and R. So you can easily see that when you add both the left-hand side here and the right-hand side here, it will be matching, right? Because P plus S is equal to Q plus R, right? And here what you're getting is 2A1 plus P plus S minus 2D. And there you will get 2A1 plus Q plus R minus 2D. And P plus S is equal to Q plus R, right? So this is one interesting property of arithmetic sequences. Also, we know some other properties. If AN is an arithmetic sequence, then B times AN is also an arithmetic sequence. What is B here? B is any real number. B is any real number. So if you multiply the terms of an arithmetic sequence by any real number and you multiply all of the terms, the resulting sequence is also an arithmetic sequence. Another similar property is if AN and BN are arithmetic sequences, then the sequence AN plus BN plus minus actually is also an arithmetic sequence. So if you have two different sequences, if you add and subtract the corresponding terms of those sequences, then you have a resulting sequence which is also an arithmetic sequence, right? Now, how do you find the sum of first n terms of an arithmetic sequence? Sn is equal to A1 plus A2 till An. Now, there is a standard derivation for this. You reverse the order of the terms and you add them, and you can prove that it will be n by 2A1 plus n minus 1 into D, which is also equal to n by 2 A1 plus An. So this is your Sn expression. The sum to n terms of an arithmetic sequence is this. You can prove that very easily, and the proof is in standard textbook, so we'll not worry about the proof so much. Let's look at some properties. Let Sn be the sum of first n terms of an arithmetic sequence then we can show the following. Then we can show that, first of all, you can say S of 3m is equal to 3 times S of 2m minus S of m. Second property is, if S of m is equal to S of n and m is not equal to n, then S of m plus n is equal to 0. And the last property is, if S of p is equal to q and S of q is equal to p, with p not equal to q, then S of p plus q is equal to minus of p plus q. Now all these three properties can be proved using the formulas that we have derived. So S of n is n by 2, 2a plus n minus 1 into d, right? And you can use, now n is 3m here. Let's look at the first property. So S of 3m would be 3m by 2, 2a plus 3m minus 1 into d. And S of 2m would be 2m by 2, 2a plus 2m minus 1 into d. And similarly, S of m, if you write m here, it will be m by 2 and 2a plus m minus 1 into d. So let's subtract S of 2m minus S of m, right? So here this term we are calculating, S of 2m minus S of m. That would be, you can take m by 2 common and you will have 2 times 2a, so 4a plus 2 times 2m minus 1 into d minus 2a minus m minus 1 into d. So what we are getting here inside the bracket is m by 2 and we are getting 4a minus 2a, so 2a, and d common, you have 4m minus 2, 4m minus 2 minus m plus 1. So this is becoming 3m minus 1, right? So notice that this term is becoming 2a plus d into 3m minus 1. And that is here, right? The only thing is, this is 3m by 2 outside the bracket and we have m by 2 outside the bracket. So that just tells you that S3m is 3 times of this, right? Because this was S2m minus Sm. So basically, using the formulas of your summation for first n terms of a sequence, arithmetic sequence, we can prove all these three properties. And those are straightforward. It's just application of the formula. So I'll not try to show you all the proofs. You can do them yourself. But keep in mind, these three properties might turn out to be useful in the future, right? Let's look at geometric sequences now. What is a geometric sequence? What is a geometric sequence? So we have a sequence an such that the common ratio of any two successive terms is same, right? Such that the ratio of any two successive terms is constant. That kind of a sequence is called a geometric sequence. So what happens here? If you write the terms here, a1, a2, a3 till an, we have a2 by a1 is equal to a3 by a2 is equal to a4 by a3 and so on, is equal to r. Let's say this is called r, this ratio. So this ratio becomes the common ratio, and we have similar terms here for geometric sequence. If P, Q, R, S are real numbers, are real and not real, they should be integers, are belongs to Z plus, and P plus S is equal to Q plus R, then AP times AS is equal to AQ times AR. This will be obvious to you if you know the general term of the geometric sequence. So the general term AN will be A1 multiplied by R power n minus 1. This is the general term of the sequence. So if you use this formula here, you will be able to prove this property. Also, the sum to n terms of the geometric sequence will be A1 1 minus R power n by 1 minus R. This is the sum to n terms of a geometric sequence. The proof is very standard and should be known to you already. Let's look at some more theory here, which is slightly more advanced. Sometimes we don't just have simple arithmetic or geometric sequences. We might have sequences which are first order or higher order arithmetic sequences. So what I want to discuss here is arithmetic sequences of higher order. So what do I mean by that? Okay. So the first thing is, let's try to understand the definition for a given sequence AN. We denote by Bn the difference of An plus 1 minus An, which is the consecutive terms of An. So this sequence Bn is called the first order difference sequence. First order difference sequence of An. So what do we mean by this? So let's say we have a sequence like this: 1, 4, 7, 10, 13, and so on. So what is the difference between successive terms of this sequence? Let's say this is my An, right? The difference between successive terms is 3, 3, 3, 3, and so on, right? So this is the difference between 4 and 1. This is the difference between 7 and 4, 10 and 7, and so on, right? So this sequence is called a Bn, and Bn is the first order difference sequence of An, right? Now you don't have to have an AP on the top. You could have a sequence here 1, 4, 8, 10, 15, and so on also. In that case, my difference sequence will become 3, 4, 2, 5, and so on, right? So for any sequence of numbers, the first order difference sequence can be constructed by taking the difference between successive terms of the original sequence, right? Okay, now once we have understood the first order difference sequence, let's go ahead and define something else. Like we have An is the original sequence. We have Bn, where Bn is equal to An plus 1 minus An, right? So this is the first order difference sequence. First order difference sequence of An. Right. And then we can define if Cn is equal to Bn plus 1 minus Bn, right? Then Cn is first order difference sequence of Bn, because it is the difference of successive terms of Bn sequence, and it is also called second order difference sequence of An, right? Because Cn, how did Cn come? We took the difference sequence of Bn, and Bn itself was the difference sequence of An. So Cn is basically the second order difference sequence of An, because you have to do 2 times differences, right? In this way, we can define a pth order difference sequence of An. Here P belongs to natural numbers. So first order, second order, you could make a pth order difference sequence of An, right? Now we come to the basic definition. We say if the pth order difference sequence of An is a non-zero constant sequence, then An is an arithmetic sequence of order P. So let's take An to be a regular AP where it is like 1, 4, 7, 10, 13, and so on. This is a regular arithmetic sequence. And you can say that the Bn that we can construct from here is 3, 3, 3, 3, and so on. So can you see that Bn itself is a non-zero constant sequence? It is non-zero and it has constant terms. So Bn is a non-zero constant sequence. And Bn was what? Bn was first order difference, right? First order difference sequence of An. So therefore, we can call An as arithmetic sequence of order 1. Arithmetic sequence of order 1. Because after doing one time difference sequence, you are getting a non-zero constant sequence, right? So it must be having order 1. Because the first order difference sequence is non-zero constant, right? Now, what can we predict from here? If sequence An is an arithmetic sequence, of order P, then its first order difference sequence, which is Bn, is an arithmetic sequence of order P minus 1. Is an arithmetic sequence of order P minus 1. And the necessary and sufficient condition for a sequence for An to be arithmetic sequence of order P, is the general term An, of the sequence is a pth order polynomial in N. So what is a pth order polynomial in N? It is a pth degree polynomial basically. So if you take a normal arithmetic sequence, we know An was A1 plus n minus 1 into D. This is a linear polynomial in N. So the sequence An, whose general term this is an arithmetic sequence of order 1, because the order of this polynomial is 1, or degree, right? But if it was a quadratic in N, then the sequence was a arithmetic sequence of order 2, right? Now, if an is a pth order polynomial in n, you will also be able to show that the sum to n terms, the sum of the first n terms of this polynomial is p plus 1th order polynomial in n. So the necessary and sufficient condition for an to be an arithmetic sequence of order p is that the general term is a pth order polynomial in n, and the sum to n terms is p plus 1th order polynomial in n, right? So this is about your arithmetic sequences of higher order. Then we also have some theory about summation of sequences. So I'll just summarize some facts that you need to know. Summation of sequences. So some basic facts are, you need to know the sum of first n natural numbers. So this is equal to n plus 1 by 2, and the second one is sum of first n squares. This is equal to n plus 1, 2n plus 1 by 6, and the third one is sum of first n cubes, and this is equal to 1 by 4 n square n plus 1 whole square. And for any sequence, for any arithmetic sequence an, we can prove that s of m plus n is equal to s of m plus s of n plus mn times d. This is a nice property that you should be aware of. M and n are natural numbers, and d is the common difference of the AP. You should try and prove this property yourself. You will be able to do it if you know the summation formula for the sequence. You should be able to prove it yourself. Another property that we should see is, if you have a geometric sequence, for any geometric sequence, s of m plus n will be equal to s of n plus q power n s of m, and can also be written as s of m plus q power m s of n. Again, these are properties that will be obvious if you know the sum to n terms formula, which is this. You should be able to use this formula to prove these properties. So you should try that yourself. I'm just summarizing the property for you. For any infinite geometric sequence, if common ratio r is less than 1, the sum to infinity is given by a by 1 minus r, where a is the first term and r is the common ratio. If r is greater than equal to 1, the sum to infinity diverges. So it is also infinity, because the geometric sequence will be monotonically increasing in that case, right? Now, in the problems of this chapter which require summation, there are many methods there are. So there is method of elimination by splitting terms. So here what we do is we express our nth term as the difference of the successive terms of some function, and then we try to sum it up and use telescoping series method to get the sum. There is also method of undetermined coefficients. However, like, it will be more useful if I actually solve problems and show you the applications of those methods, right? So the theory that I wanted to cover is what we have done so far. So we have looked at arithmetic sequences, geometric sequences, basic definition, and some basic properties. We have also looked at arithmetic sequences of higher order. So higher order arithmetic sequences happen sometimes where you could have a pth order arithmetic sequence where the difference of the an term will be a pth order polynomial in n, and the sn term will be p plus 1th order polynomial in n, right? And then you have some basic facts about summation of series, which you need to know, and some properties that are relevant for our problem solving. So that's about it for the theory section for this chapter. And what we will do now in the next video is solve a few problems and get used to problem solving using sequences, right? So stay tuned, and I'll see you next time with problems for this section. That's all for now.